All right, Lars, take it away.
Okay, great. Thanks and welcome everybody. If you joined after we welcomed the first batch of people. I'm happy to introduce Siqian Shen. Siqian is an associate professor of industrial and operations engineering at the University of Michigan, where she's been doing lots of research in stochastic and robust integer programming, also network design and optimization, with main applications in energy, transportation, and infrastructure. And for her work, she's been the recipient of the DOE Early Career Award and the IIE Pritzker Doctoral Dissertation Award for her PhD work. And today, she's going to tell us about some modern facility location problems and how to address them. Go ahead.
Okay, I will share my screen.
Yes, please.
Okay.
Looks good.
Right. Okay, thank you. Yeah, thanks for the nice introduction. Also, thank you for the invitation for this great, organizing this great, series of talks. So today I'm going to, mention a few papers that I have with co-authors recently on facility location problems. So I intend to make this talk a bit sort of like a technical light. And at the end, I'm going to mention, some related COVID-19 applications that we're thinking about extending the work. So welcome to, sort of like give questions, comments. A lot of these papers hasn't been published yet. The best we have so far is sort of like a major revision. So, welcoming any kind of comments as well. So as you notice, there are 3 parts of the talk. I'm going to, focus on 2 today. The first part is the facility location involving competition. So that part is an ongoing paper, and then I decided not to include into today's talk given the time limit I have. And then, I'm going to focus on facility location with prioritization and also decision-dependent demand. So first, I would like to thank, whomever funded us to do these things, and also my collaborators. So along the way, I'm going to introduce different topics, and then I'm going to mention the papers that I have with subset of these people. So, but then, yeah, first I would like to recognize them. And actually, I want to also broadcast for Bastie's talk. So Bastie, she's the next week speaker. I believe she's the first speaker next week. And she's going to talk about something like very, very cool things that she does with Shabir and her co-authors. So, welcome to join her talk as well. But I'm going to mention a paper that I have with both of them today. All right. So the outline of the talk today, as you see, will be focusing on FLP with prioritization, and then we move on to endogenous demand, which, you can think about the demand depends on your decision. So the first part, let me introduce this problem, which I think everybody kind of like knows. This is a normal sort of like setup I have for undergraduate course, that you have a facility, which you can look at as a network. And then your demand is like distributed around the network. With uncertainty, you actually don't know where they are and how many are them. You have a few sites that you can open facility. So you have binary variable to say, do I open facility or not? And then you will have some other variables to represent shipping decisions from your open facilities to your demand. So the goal here, of course, you want to satisfy the customer demand as well as minimizing the total cost. And you can introduce many variants of this type of problem. Say if you have uncertainty, then you can have recourse decision. Once you see the uncertainty, there's something you can do to change your decisions and so on and so forth. So I'm going to, examine individual sort of like a variant of this FLP problem later along my talk. Some new features you can consider, and then actually people already consider in the literature for quite many years. So one interesting problem is you look at this problem as a competition, and that kind of relate to what our first speaker was talking about. There's like games related here. Well, in this particular setting, there are many kind of variants. You can look at them as equilibrium, or you can look at them as sequential games. And then there are many different ways of modeling the problem. In particular, we have a paper related to sequential competitive facility location, and you look at the customer choice as a utility function. So then there is some uncertainty and also ambiguity related to this utility function that you need to address. So in that paper, we basically formulate the bilevel programming problem into a MILP. And then further, we for solving that MILP, there is some function you can actually prove submodular, so you can apply submodular cuts and auto approximation cuts to speed up computation. So for the details of that paper, because we're close to put it online. So yeah, if you're interested, just send me an email and I'm happy to send a link once it's ready. But I'm going to omit here today just because this talk is less relevant to the COVID-19 that I'm going to talk about at the very end of the talk. And then the first one I'm going to talk about is what if you have prioritization decisions you have to make once along the way when you try to locate facilities. So the idea of that is basically you have some budget to open facilities, but then that budget is not known to you when you make a decision. And that budget can vary along the years. So you're actually facing some sort of like a multi-stage decision-making problem that with a random budget, how you prioritize. And we will introduce more details around that concept a little bit later. The other idea is that if you have facility location problem, instead of assuming you have some sort of like exogenous demand, the decisions you make, in fact, will change how your demand respond to you. And application here is a car sharing problem that I have been working on for several years, that in fact, where you choose the location to park cars will highly affect how people utilize your service. So that's kind of like the motivation there, and then we have some results over there, okay? So first, let me start with this FLP with prioritization. The idea was borrowed from this paper, a very, very nice paper published by Ali and David Morton a few years ago in management science. And then the setting there was more sort of like, you can call it a two-stage or one-stage problem, but you have uncertainty. So the motivating example here is basically a K-median problem. You can consider some sort of like military demand that you have to satisfy, and then you have the budget to allocate your facilities. And then this first picture basically shows you that if I give you one facility budget, say you can only open one place to satisfy the demand over the grid, and there are certain assumptions that the author make in terms of how the demand distributed. This central place is the optimal solution. But if you're allowed to open two, and of course, you know, these two becomes a better choice to split the demand. But then that means that if I change my mind, if I gave you one before and then now I tells you you can open two, this one that you already built is kind of like wasted, right? So the idea here is that how can we incorporate some priority idea, meaning that the decision you make is not the location you would like to put, but a list that you can give it to me so that I can go through the list as I look at my budget. And so in that way, basically, it's better to, well, in my opinion, you know, so that it can be more justable if you have this multi-stage setting, because the decision have to be repeated over the years. And then for the decision maker, they don't have to solve a multi-stage formulation sort of like repeatedly, which is very time consuming, has this curse of dimensionality problem. Instead, the list is kind of like a policy to them. Okay, so in their paper, they basically say that if you gave them a priority list instead of asking them to open, you know, the best facility location, then this is the first one. So you gave them a list, and then if they only have one budget, they will locate here, okay, as number one. And if they turns out to be having two budget, then they can locate another one. And you can see that that solution is different from the optimal solution you see before, which means that if they don't have the chance of opening the second facility, they are kind of like a little bit, you know, far away from the true optimal solution they can achieve. But that's basically a sacrifice they have to make. Okay, so the priority list gives you more flexibility in terms of making decisions. So then, you know, we would like to incorporate that priority list concept into multi-stage facility location problem. And then the decision basically, you know, you can think about Amazon, they are trying to allocate their warehouses globally. and the budget they have for the next 5 or 10 years are uncertain. So then like, can they come up with a priority list so that they know under what budget what's the best solution? And basically that's what you need to obey when you make the decisions. The advantage of doing that, then you kind of like, as I said before, you come up with a list at the beginning and you just commit yourself to the list basically. And then there are many ways to do that, in fact, in the multi-stage setting, and you will see that we have several different models for that. So, so here are the 3 cases we have considered for this sort of like a FLP with prioritization thing. So the setting of the FLP is the following. As you can see, I'm not going to explain the details of every single parameter because I think they're very self-explanatory once you see the model. Just notice that for the typical FLP, you don't have the time index t, but because we're considering multiple stage here, then you consider you're making the time, you're making the decision over time from 1 to capital T. Your uncertainty comes from 2 sources. So normally you have this demand uncertainty dt at each time period t, and that uncertainty is being, so we assume that you can sort of like, the uncertainty you're facing is the uncertainty at the end of time period t minus 1 or beginning of time period t. And also for the future, how much budget do you have for the future? So the BT budget is for that particular new period that you are facing. So instead of the random demand we usually consider, right now we also consider you don't know what the budget is. Okay, so the both sides will give you uncertainty. The decision variables here are x and y as we usually have. We introduce a set of decision variables as S. So this S decision variable is in fact telling you what the priority list looks like. So if the location I prime, it has a less priority than I at period t, then basically, you will set this ST I prime equal to 1, but then the other way around equal to 0. So then we also do not require to compare every pair of facilities priority at every single stage, just because, if your budget don't need that many, you don't necessarily need to set their priority at the very beginning. So then, both of them can be equal to 0 if they're, you don't need to compare them. So to formulate a problem, we consider some sort of what we call scenario tree in multi-stage stochastic programming, which will result in very large scale mixed integer linear programming we need to solve later for the multi-stage problem. So if you look at, what kind of cases you can compare here, the first one is very obvious if you don't have this priority. So you are not constrained, you just solve a multi-stage formulation. And in this formulation, you just need to decide where do I open facility for each type of period, because you can dynamically change your decision. And once you see the uncertainty, more information, and then you can sort of like, make more decisions along the way. The other setting you have here is we call changeable priority. So if I decide some sort of like priority as 0 at the very beginning, and notice that this small x right now is a vector. So include all the S, T, I prime variables I have, but then that's T equal to 0, right? But you are allowed to change the priority as far as they make sense. So I would explain what kind of, changing makes sense and what doesn't later. So then, you can flexibly decide different type of priority, because for every time period, the decision maker only need to commit to the current priority list that they have. Or you just say, okay, can I just fix all the priority? And does it make more sense? Because you just want to kind of like, regardless new information you receive later, can I use the same priorities throughout the time? Okay, so I think the most, I'm going to model the problem later, just use this changeable priority case, and then you can see that it can easily be, modified and set to the no priority or the fixed priority case, okay? So here, basically you have this typical multi-stage formulation setup. I'm going to ignore the details here. You have state variable and stage-wise variable, which means that whether these variables are linking two stages, neighboring stages, or they're just the variables within their own stage, okay? And then the constraint I have for the changeable priority case, as you can see here, you need to decide, each pair, you need to decide the priority at the beginning and also the later time period. And you only need to prioritize those facilities are unbuilt yet, right? Because they have the chance to be built later. And then also we need to avoid a cycling constraint here. So those variables, constraint, as you can see, are purely formulated based on this, like S and X variables. And then we use that to pass to the feasible region of the Y variables with the shipping variables. And here, basically, you just need to follow some rules of saying, if you already build your facility, so if you already have your priority list, the building decision needs to follow the priority list. Basically, this is what it says, and you can verify those details. But as you can see here, if I include more constraint, basically these are non-anticipativity constraint, then I can make the changeable priority to fixed priority case. I'm just requiring all the priority to be the same. And then, it's also very easy to see that, the objective function of different cases, what they correspond to. So the feasible region of no priority, so Zn is no priority, Zc is the changeable priority, and Zf is the fixed priority. Their feasible region gets shrink and shrink, right, over time. And then basically, we should anticipate this kind of objective function. So at this, I just want to show you some very preliminary numerical results that it's not talking about how do you solve these models and making them more efficient and stuff like that. I just want to convince you that having the priority list is something that sometimes is useful. So how do we solve this type of problem? We have multi-stage mixed integer linear programming. You can solve the LP relaxation and run the integer solution using SDDiP. So stochastic dual dynamic programming. What we use is a step further called SDDiP, borrowed from Shabir's recent paper with his co-authors. So basically that's a technique that you can using forward and backward steps to improve the solution time of multi-stage stochastic integer programming. So I want to show you these two pictures. So the first one is basically if I compare changeable with non-priority case, because I just want to know, does it make sense to include this sort of like a priority at the first place? And you can see that for most cases, and in this case, it's about 70 of the instances that we compute, they're quite similar. So even you allowed yourself to, commit to, like you have to commit to a certain priority, the objective function doesn't suffer that much. But then in some cases, if they are different, because I mentioned before that you're just basically restricting yourself to more constraint, and then the objective could kind of suffer quite a bit, as you can see for the case that are not the same, their objective function. The other one is just saying, does it make more sense to allow you to change priority over the time, or just fix one at the very beginning? Again, with the instances that we tested, most of the cases they're very similar, but if they're different, they have huge difference. So we're planning to explore more different cases and just kind of reflect when it makes more sense to change priority, when doesn't, and so on and so forth. For this work, I anticipated to put online sometime later this summer. Okay, so now I move on to the other part, which I said before that we consider endogenous uncertainty in the facility location problem. So the motivation here is car sharing. If you have like a nearby location that rent cars, then you're more likely to use the service, right? But the question here is like, how can we adapt this into the model, and what kind of model best describe this setting? So the way that we think about this problem is that, first of all, I would like to characterize the how can we model the impact of facility location decision on customer demand distribution. The way we're going to describe this is use something called moment ambiguity set. So we're going to use this distribution robust concept to strategically determine the facility location under this demand uncertainty. But because this uncertainty is kind of like you go as you learn, so they are not really sort of like the distribution of that is not very available at the very beginning. So we would like to use the distribution robust idea. So this is a joint work with Basti and Shabir under major revision to talk about sort of like the decision dependent demand for facility location. So just, so like as many of you probably already know, for DRO, distribution robust optimization, there are many ways you can categorize the unknown demand distribution. And then, like some papers talk about these sort of like a distance-based ambiguity sets, Wasserstein or, phi divergence. Some others use moment-based ambiguity set. So in this talk, I'm going to focus on the moment base. So basically the setting here is the following. You assume certain probability associated with different discrete demand. So again, if your demand is continuous, we use sampling approach to focus on a few different demand levels. And for these different levels of demand, we have different probability for different location as well. And then we're going to kind of like bound the first moment and second moment within a certain category, meaning that I have some sort of like empirical mean value of the demand and empirical standard deviation or covariance. You can model also covariance. And then basically I'm trying to say my true mean and true standard deviation is not too far away from the empirical value I know. And then you can use certain parameter to adjust the robust level of this ambiguity set. So then, like the question here from standard DRO is that right now your mean value and the empirical value that you have is actually themselves is a function of your decision. So in here, our decision variables are Y right now. So then you can see that my mu is no longer like mu J, but instead it's a mu J Y, which is a function of Y. So the question is, how do you set up these functions? And again, depends on what kind of basically, it's the applications that you're talking about. In our case, we focus on sort of like, if I open more facilities, I hope to see more market demand. But then there is always sort of like some cap that, it will just saturate over there. So you can sort of like set up these functions in this way as a step function or piecewise linear function. And then the takeout here is that for this overall facility location problem, you have to minimize your the cost of your location plus some worst case second stage cost, because if you choose a facility in a too bad way, with respect to this ambiguity set, you're going to see some worst case performance. So you can set up this formulation as a min-max model this way. And the normal way is to take the dual of the inner maximization problem, right? But then what we see here is that one proposition we show that is our problem can be fully decomposed by the location. So then you have an easier problem, max problem for every single location. But then once you take the dual, you're going to run into the problem of mixed integer nonlinear, because there will be bilinear and trilinear cases. So eventually you end up solving this giant mixed integer linear programming problem if you substitute the nonlinear part with the McCormick inequalities, okay? This is the one minimization problem because we take the dual of the inner maximization problem. So some other things that we did in the paper was to sort of like propose some value inequalities that you can show very effective to improve the solution time of the MILP. I'm going to skip this numerical results though, because I think I'm out of time. But basically this numerical result tells you that does it worth to include decision dependent into a typical DRO setting versus you don't have decision dependency versus you don't assume there's ambiguity. So you use some nominal distribution to solve your problem as a two-stage stochastic programming problem. We mark the one has the best objective, actually quite substantial best objective in the auto sample test, and that's our DDDR model. And also if you compare the demand being unmet here, the DDDR also has a very low sort of like a number in terms of the demand I didn't meet except the last one, but then the last one compared to the other ones are much better as well. So the the result kind of like definitely says that if you think this setting is what it is in the reality, like your demand depends on the uncertainty, you should really use that. Okay, so the conclusion part is that, like for the first prioritization work, we focus on the modeling more and directly use SDDiP to solve the model and see how we can model prioritization better. The second part basically use some other tricks like value inequality and stuff like that to improve the computation. now I want to mention, like some new application we have been thinking about. And again, like we have many experts in the audience who are, IP expert, integer programming, machine learning, and a facility location expert. We should all, sort of like try to apply something that we know to solve this very emerging application, which is the COVID-19. So if you think about this, testing location, facility location problem, right? It's often the case that a country doesn't know how many tests they actually have, like in terms of the resource or how much budget they can have in the future to do this. So then it's a very natural sort of like facilitation with prioritization. If you can have a prioritization list to the policymakers, and then they just need to, look at the budget they have for different states or different counties, and they just like go through the list and then open the ones that they can open, it will be beneficial for them. The other ones that I think very important is that the data that we see these days are not true data, because you don't have enough testing, and then it's reflected in what you observe in terms of demand. So a natural way is to think about how your actually observation can be dependent on your decision of where to locate a testing facility and how many to locate. And then it can be modeled as a demand-dependent, decision-dependent demand case. Okay, I would like to, just kind of like confirm. I think these two problems are definitely something a lot of countries are doing quite well. The picture I show here is one is Singapore, so they actually have their testing facilities being marked on internet on a map. So then the public can see where they can get tested, and then the real time sort of like capabilities they have there. And then it's very convenient for them to book, kind of appointments and so on and so forth. Versus in the US, I think most of the time we just see like a big map telling us how bad it is in terms of infections in different states, county, but not like further information. So then, I think these models can help you to reflect more information. And that goes also to some, if you're interested into some sort of like COVID-19 related research, I think, so I put some in my online document, and then there is also a sort of like the slides I have, which talk about more about the EOR models you can do. But at the very end, there summarize some sort of like the data set that people have. And one of the place that you can go, I think it has a very nice visualization there, is this like outwardingdata.org. And then it will show you that, for instance, different the trending of the COVID-19 in different countries. And then, how do we know our testing is enough or not, right? So there are a lot of like, pictures. And in one case I really like is this one, like the number of tests per confirmed case. So you can see here that for the countries that are doing quite well in terms of managing, kind of like their spread, the disease spread, they have ample tests. To find one case in Vietnam, they have done 788 tests. So it's a very massive testing, versus if you look at, say, the US case, actually for every 5.8 tests they did, they can find one. So it's definitely not enough here in the US and in many other countries as well. So yeah, we should, there are a lot of things that OR people can do for improving testing and then other things. Okay, so I think I'm done with my talk. Thank you, and I'm happy to take any questions.
Okay, thanks, Siqian. Thank you very much for a nice talk. If you have a question, please either type it in the chat, or you can raise your hand, and then we can unmute you to ask it by voice. So I have a high-level question. In machine learning or in reinforcement learning, people typically see this, sequential decision-making problems, especially when there's uncertainty or stochasticity. They see, these as natural kind of test beds for reinforcement learning algorithms. where, you know, the action space is a discrete space, similar to the discreteness that arises in your MIPS. So have you thought, or what's your perspective generally on you know, these two kind of perspectives?
Yeah, I think that's interesting, and we do explore a few different other ways of modeling these days with respect to that. And actually, we recently have a paper I also put online that it's all again under major revision right now, so it's not published yet. But it's called Distribution Robust Partially Observable MDP. So and then, you know, we search there are a lot of papers so in machine learning area, you know, also talk about robust POMDP, robust MDP, and some other things, right? And I agree that, you know, the methodology is like, how do you model it? It can be different, but then essential problem I think are similar. However, I do think that depending on what kind of problem and decision variables we're dealing with, as well as how complicated the constraints, right, are. In my opinion, I think if the problem formulation like itself has many constraints and has a lot of like structures and stuff like that, I would prefer more using, you know, typical IP setup plus, you know, uncertainty. So there's more like a multi-stage stochastic integer programming, because I feel like if you want to kind of like have some reinforcement type of settings, the update needs to be very quick, and that's usually hard to adapt to a problem that has many constraints and also very complicated decision. But then, you know, if the decision is like, oh, you can easily observe how your state or in terms of like the feasible region, right, how they transit to different types of state of the system because of your action. If you can have a clear sort of like understanding about the you know, transition matrix and also the observation matrix, I think, you know, using MDP, POMDP, or reinforcement learning are making more sense there.
Cool. So we have a question in the chat from Leila on prioritization. So the question is, how do you model that demand becomes more known over time? Do you use some update function on demand distribution?
Yeah, so I need to clarify that, you know, the 3 talks I plan to talk, and I didn't talk about prioritization, I'm sorry, the competition today. They are independent work that we have. So for the prioritization part, we assume that we know the uncertainty of the demand. So then basically, if you look at this scenario tree that I drew before, right, this is my scenario tree. So basically, you know, I know the path from the beginning to the end for every single path, like how much demand are there. And I agree with you, they can be integrated. So meaning that, you know, sort of like I'm working on this multi-stage problem with prioritization, but at the same time, as I go deeper to the path, I'm learning the demand at the same time. And that just requires more complicated modeling, yeah. But we sample the path like to the very end at the very beginning. So I know exactly at every node what the demands are. However, when I'm at this node, I don't know the future demand, right? So that's a difference, yeah.
Okay, and any other questions?
I have a question, but I can't figure out how to raise my hand. So I'm just gonna jump in. So in this part of the first part of the talk with the prioritization, if you compare the solution from the prioritization to maybe the optimal solution, if you are able to place K facilities, is there a guarantee on how those objective functions are different?
Yeah, so that would be the next step. Right now we're exploring very early on, which is like the modeling part and the computation part. I would love to work on something more theoretical in terms of, you know, sort of like, how would you characterize the bound between, you know, how you're worse off, right? Given you have to be following this priority list. Something that I think, you know, people can follow first is, Shabir has a few papers long time ago, actually, with his co-authors on his website about characterizing bound between the multi-stage and the 2-stage stochastic integer programming for some capacity expansion problem setting. So the problem structure has to be pretty strict. It's a capacity expansion problem. There is no priority at all in that setting, but then basically saying that how much you gain by allowing yourself to do decisions multiple stage versus you have to commit a decision at the very beginning. So in a two-stage setting, right, you don't know the uncertainty in the future, but you say that, you know, at time 1, I'm going to, you know, decide this capacity, time 2, this, but you have to commit from 1 to t at the very beginning. Instead, you can say, I make 1 only, and then I go ahead, go to 2, and then once I see more demand information, I make 2, and so on and so forth. How much you gain by doing that? And then they have very nice result in terms of bounding the upper bound and the lower bound side. So basically, you know, like, you know, if you're worse, how worse you can be, basically, right? And then very intuitive, the setting over there tells you that if your demand is more volatile, which means that if you have a higher variance, you should expect better performance of the multi-stage setting, because you are allowed to observe more information versus the lower variance doesn't gain you much. So their setting is, you know, they have this quantity bound telling you how you can measure the gap. But I think it becomes more complicated once you have other decisions like prioritization.
Thank you.
Yeah, thank you.
I guess let's thank Siqian and Sharam one more time.
Thank you.
And I'm going to stop the recording now.
Yeah, thank you.